Hello, I'm Professor Chuka Ngoye, a professor of regenerative chemical process evaluation and empirical modeling. Today, we're going to look at energy analysis as it relates to manufacturing processes. We know that energy input during manufacturing of goods and services is very, very important. It is important to know the gross energy requirement for production of some engineering materials, engineering metals and alloys from their primary sources. And so this model was derived using experimental results obtained from such analysis. Now, in this model, we can see that from all indication, it evaluates the tensile strength of engineering materials based on the gross energy requirements. When we talk of gross energy requirements, we mean the summation of the energy that's required to process the material from the primary stage to the finished stage. Now, this model is applicable in manufacturing processes such as manufacturing engineering materials like cast iron, steels, brass, aluminium, and duralumin. These are materials where this kind of model can be applied, where the tensile strength has a direct relationship with the gross energy requirement. Now, we can see the value of the gross energy requirement measured in gigajoules per T, while the tensile strength is measured in gigajoule per meganewton. In this model, we have two empirical constants. N is equal to 0.33 and K is equal to 0.5. When these two empirical models are substituted in the model, it has a way of varying any process material that we want to calculate, depending on the change in the other parameter. Now, let us go into the problem solving concerning this energy requirement and its relationship with tensile strength of the material. Now, the question says, calculate the gross energy requirement if the tensile strength is 2.03 gigajoules per meganewton. And then the empirical constants are still the same. N is equal to 0.33, while K is equal to 0.5. When we substitute these values into the model, we'll have this, and that's exactly what we have in the first page of the screen. Now, we want to solve this problem mathematically the same way every other problem in math can be solved. And so, based on that, if we divide both sides of equation 1, this is equation 1, and if we divide both sides of equation by 0.5, we're going to have 2.03 over 0.5 to be equal to the value of the gross energy gross energy requirement raised to power 0.33. And if we evaluate the left-hand side of equation 2, which is 2.03 over 0.5, we're going to have 4.06 to still be equal to the gross energy requirement raised to power 0.33. That's equation 3. Now, our mission is to calculate the gross energy requirement value. And so, in order to continue, like I said, we are going to approach it mathematically. The only way we can do that is to take logarithm of both sides of equation 3. And that will give us log 4.06 to be equal to log gross energy requirement raised to power 0.33. And if we go further to evaluate the logarithm of both sides, we shall have that log 4.06 will give us 0.609 to be equal to, then based on the law of indices, the power 0.33 to which the gross energy requirement is raised. Now we multiply log of the gross energy requirement. So we have 0.609 to be equal to 0.33 multiplied by log of the gross energy requirement. And then, based on that, if we divide both sides by 1.84, because the logarithm of 0.609 is 1.84, and so if we now divide equation 5 by 0.33, which is this, if we divide equation 4 by 0.33, we're going to have 0.6. We're going to have 1.84 divided by log of gross energy requirements. And then, based on that, if we take the antilog of both sides of equation 6, that is this. If we take antilog of 1.84 across log E, we're going to have the gross energy requirement to be equal to 10 raised to power 1.84. And on further division or further evaluation, we're going to have the gross energy requirement is equal to 69.18. And so we can make can summarize our calculation by saying that the gross energy requirement now for a case where the tensile strength is 2.03 is 69.18 gigajoules PT. I'm still the instructor, Professor Chuka. Thanks for listening, and keep watching and subscribing to Systems and Process Maths eLab. Bye for now.